Hello everyone. Today we shall discuss about mechanical properties of fluids. From the microscopic shear of stress of honey to the aerodynamic lift of a Boeing aircraft. Definition: liquids and gases can flow. Unlike solids, they possess no definite shape of their own. The defining characteristics: shear stress. In case of solids, resist shear stress. Shape changes only slightly under force. Fluids offer very little resistance. Shape changes continuously under application of even very small shear stress, approximately 10 to the minus 6 times that of solids. Key concept: the difference between a steel beam and water is resistance. The difference between a steel beam and water is resistance. The physics of pressure. We know that the pressure can be defined by force by area. You see here, a small area we create a high pressure here. Large force, moderate area. Force distributed, safe pressure. You see, this plank, the force is distributed along the plank, so the man is safe here. You can see here force is always normal to the surface. Normal. Remember that force is always normal to the surface. That is important for us. Pressure is a scalar quantity. It is a component of force, normal, perpendicular to the area. So it is a component of force perpendicular to the area. Pascal's law. Pressure in a fluid at rest is the same at all points if they are at the same height. Pressure in a fluid at rest is same at all points if they are at the same height. Whenever external pressure is applied on any part of a fluid contained in a vessel, it is transmitted undiminished and equal in all directions. This is given by Blaise Pascal. Whenever external pressure is applied on any part of a fluid contained in a vessel, it is transmitted undiminished and equally in all directions. Forces cancel out to prove equal pressure in all directions. Engineering giants, the hydraulic lift. Here you can see the power equation is F2 equal to F1 A2 by A1. A2 by A1 is a mechanical advantage. Real world impact, a small input force lifts 1350 kg by amplifying pressure across a larger surface area. So here the pressure at this point is P1 F equal to F1 by A1, F1 by A1. And here the pressure will be F2, pressure will be F2 by A2, F2 by A2. But remember that the pressure P1 and P2 will be equal according to the Pascal's law. Since P1 equal to P2, P1 is equal to P2, therefore we can write that F2 by A2, F2 by A2 is equal to F1, F1 by A1. Or you can write is F2 is equal to A2 by A1 into F1. So we can find that this A2 by A1 is called the mechanical advantage. If we increase the area, suppose if the ratio of A2 by A1 is equal to 1000, so you can see here that F2 will be 1000 times of F1. So the force F1 is multiplied 1000 times here by factor 1000 times, and you get the force F2 as 1000 times. And this is the hydraulic lift. In this way, hydraulic lift works according to Pascal's law. The next important thing is the weight of the ocean, pressure and depth. Here you see absolute pressure is P, Pa is atmospheric pressure, rho Ga is density into gravity into depth. So the hydrostatic paradox is pressure at the bottom depends only on height, not on the shape of the vessel. This is the hydrostatic paradox. Pressure at the bottom depends only on the height, not on the shape of the vessel. You see, all the pressure at this point, or this point, or this point it is same. This is hydrostatic paradox. Depth data: 10 meter depth, 2 atm pressure, 1 kilometer depth, 100 meter pressure, submarine crash depth. This can be found out. So the weight of the ocean or the pressure and depth. The hydrostatic paradox: pressure at the bottom depends only on height, not on the shape of the vessel. The dynamics of motion, flow motion. We hear two types of motion. One is laminar flow or streamline flow, and one is turbulent flow. Steady flow, predictable, layers slide smoothly and is slow also. And here you see critical speed threshold. In case of turbulent flow, chaos exceeds critical value, critical speed, whirlpools and white water. You find here this is the turbulent flow, and here in this case the speed or velocity is more than the critical speed, critical velocity. Conservation of mass the continuity. The AV is equal to constant. Incompressible fluid must speed up when channel narrows. This will be speed up. Channel narrows, the mass in is equal to mass out, and that is the conservation of mass or continuity you can say. So speed increases at this part, decreases at this part because A1 P1 equal to A2 P2. A1 P1 equal to A2 into P2, and this is the equation of continuity. This is the equation of continuity. Speed increases at this point. Bernoulli's principle, the conservation of energy in fluids. That is important. The conservation of energy. There see the pressure energy, the kinetic energy per unit volume, pressure potential energy per unit volume is equal to constant. The counter initiative inside as fluid velocity increases, pressure decreases assuming constant height. So this is valid for November. It is non-viscous, incompressible flow in interregular cool state. Right? So what we get is Bernoulli's principle, this P plus half rho V square. Half rho V square is kinetic energy per unit volume, and rho GH is the potential energy per unit volume is equal to constant, and this is known as Bernoulli's principle. This is known as Bernoulli's principle. Bernoulli in action, Torricelli's law. You see here that V is equal to square root of 2G. V is equal to the square root of 2 into G into H. This is the Torricelli's law. The speed of a flux. The water jet behaves exactly like a freely falling body dropped from the surface level. Gravity is the driver. So the water jet behaves exactly like a freely falling body dropped from the surface level. Gravity is the driver. The physics of flight, dynamic lift. Here you see high velocity, interregular, the lift is there. Why? Here you can see the high velocity means it creates a low pressure zone in this region, low pressure zone in this area. And here you see the low velocity means it is a high pressure zone. So there is a drift from high pressure to low pressure, high pressure zone. So there is a lift in the upward direction. Crowded streamlines, higher velocity. Crowded streamlines means it has higher velocity. Higher velocity creates low pressure according to Bernoulli. Result, upward pressure difference. There is a pressure difference. So the pressure, this is low pressure, this is high pressure. So there is a lift in the upward direction. A 330,000 kg Boeing aircraft stays aloft with just an 8% speed difference between the upper and the lower wing surfaces. This is the physics of flight or dynamic lift. The second one is viscosity or internal friction. Here you see that viscosity eta is the resistance arising from relative motion between fluid layers. This moving the force, here is the force moving top plate, V is maximum. So material water viscosity is 1, blood 2.7, glycerin 830 thick. So the viscosity of material differs from one to that of another. Distance from bottom, you see the velocity at the upper top is maximum, and slowly the velocity is decreasing, and at the point of contact the velocity is 0. Fixed bottom plate velocity is 0 at that point. That is viscosity. Now terminal velocity and Stokes law. Here you can see that Swiss engineering precision or traction. In terminal velocity, you have to find the Stokes law. Gravity accelerates, drop. Speed increases, viscous drag increases. Viscous drag is that gives to force balance terminal velocity. Here you see that gravity is equal to that of buoyancy and viscous drag. And viscous drag can be found out by 6 pi eta v. This can be F is equal to 6 pi eta a into v, where a is the radius of the sphere, where a is equal to radius of sphere, radius of sphere. The raindrops, why raindrops don't hit like bullets? The fluid air fights back, right? So with the buoyancy and this gravity, force of gravity, the force of gravity is equal to force of buoyancy plus force of viscous drag, plus force of viscous drag, and this is at equilibrium. And at in a particular point we get the terminal velocity when this force and this force, net force is 0. When net force is equal to 0, net force equal to 0, so force means m into a 0. Since m is not equal to 0, m is not equal to 0, acceleration equal to 0. And whenever acceleration is equal to 0, the drop, this sphere has a fixed velocity, or velocity is constant. So the drop goes in the liquid with a constant velocity, right? So the velocity is constant, and that constant velocity is known as terminal velocity. That constant velocity is known as terminal velocity, right? In this way, you can find the terminal velocity in Stokes' law. Surface tension and energy. You can see here the molecule deep inside, net force is 0, right? The molecule at surface, net inward pull. There is an inward pull in the molecule at the surface, inward pull. You see, these are the forces. So there is a net force in the downward direction. Spherical water drops. These are due to surface tension. Insects walking on water due to surface tension. Capillary rise in plants. All are cases of surface tension. Liquids behave like stretched elastic membranes to minimize surface area. Key equations summary. You see, we find that pressure equal to force by area, right? Number 2, hydrostatic depth. Cool state hydrostatic depth is P equal to Pa plus rho gh. P equal to Pa plus rho into z into h. Continuity, that A1 V1 equal to ATP to the equation of continuity. Bernoulli's principle equal to half rho V square, that is P plus half rho V square plus rho gh is equal to constant. P is the pressure, the sum of total pressure, kinetic energy per unit volume, and potential energy per unit volume is equal to constant. Force Stokes drag equal to 6 pi eta AV. F equal to 6 pi eta A into V. And tertiary flux equal to V is the root over square root of 2 root 2 gh. These are the some of the important points in these these mechanical properties of fluids. So these are the various important things we have discussed. Thank you everybody for watching this video.